Hello, welcome back. This is Calculus by Dr. Oz. Today, we're going to practice another application of definite integration. It's finding the volume of the solid by using the shell method. And we're going to revolve the region around the y-axis, the given region around y-axis. And that's going to be a solid, obviously, after the revolution. And we're going to find the volume of that. So what is this region made of? Let's see, we have y equals x cubed. That's a curve. Y equals 8. That's a horizontal line. And x equals 0 is y-axis, the other name of y-axis. So let's see what the region looks like quickly. And this is the region, this is the green region, and we're going to revolve this region about. And as you see, like on the right, the region is bounded by y equals x cubed, which is the blue curve, and we have the purple line, that's y equals x, and we have the y-axis. All right, so let me just show you what the three-dimensional object looks like. Just revolve this around, you get a bullet-like three-dimensional object, and you're interested in finding the volume of this shape. So, but this time, since in the statement of the question, it's mentioned that we're going to use the shell method. So we want to remember exactly how the shell method works. In fact, we take slices horizontal to the axis of revolution, since y-axis is the axis of revolution. So we're going to get vertical slices within our green region. But let me just remind you the formula for that. Here we go. This is the table of the volume of a solid of revolution by the shell method. Okay, we have two different kinds. In one case, axis of revolution horizontal. In the second case, it's vertical. And as I said, we are in the second case. So look at the second column and the second picture here. So we got this yellow rectangle slice within the region, and we're going to revolve that around the y-axis. Okay, so this is exactly the bigger version of this picture. So to be able to write down the volume of the shell after the revolution, so you need the radius of the bottom, which is p of x, and you need the height of the shell. And this shell comes with thickness dx, the way we set it up, because we got a vertical slice to work with. All right, so 2 pi times p of x, that's the circumference of the circle. If I multiply it by the height h of x, that's the surface area of the shell. And if I multiply everything by dx, which is the thickness, I got the volume of the representative shell. And if I integrate that from a to b, that's in fact the interval where the x values range within that light blue region. So we get down to the volume formula. All right, let's start. So we're going to use the shell method to write and evaluate the definite integral representing the volume of the solid generated by revolving the plane region. We have 3 different curves provided to us. One is the cubic here. This one is a horizontal line, and then this one is y-axis. X equals 0 is the other name of the y-axis. And we're going to revolve this region about the y-axis, okay? So, and we are specifically told to use the shell method, not the disk or washer method, okay? Well, first of all, if you have your graphing calculator with you, why don't we go ahead and graph the region. You can pause the video anytime you want, and you can just like finish graphing. Now let me just show you what I got here. All right, so I have y equals x cubed right here, the blue curve. Okay, so it's right here. This is y equals x cubed, and I have y equals 8. Y equals 8 it is the purple line, horizontal line, and the y-axis. Okay, y-axis is right here. So we're talking about this green region to be revolved around y-axis. Okay. So let's see what kind of three-dimensional picture we get at the end. Okay. So this is our region. Okay, so we're revolving that around, and this bullet type shape, as you see, and eventually you get this three-dimensional object. So our goal is to find the volume of this three-dimensional object. Okay, just go backwards for you to see again. Okay, and we are specifically told to use the shell method, and in the shell method, we use slices parallel to the axis of revolution. Okay, so since y is vertical, y-axis is vertical, I'm going to get a vertical slice, representative slice, and I'm going to revolve it around and see what I get. Okay, so this is my representative slice. I'm going to revolve it around. I'm going to get a shell, right, with, let's say, thickness dx. So let's say like this comes with thickness dx. Okay, and then I have the slice only x units far from the axis of the revolution. Okay. And let's just remember the formula for the volume of the shell method. So all we need is the radius of the bottom. The radius of the bottom. Let me just use this color here. Radius of the bottom. This is the axis of revolution about y-axis. So we're in the second case. So we're right in this formula, right on my left. Okay. So all you need is the radius p of x and the height of the shell. Okay, radius of the bottom and the height of the shell. And then the formula goes like this: 2 pi times p of x, that's the circumference of the circle after the revolution, times the height, okay, and times dx, that gives you the volume of that representative shell. Okay, so for that reason, so this is so I need p of x. So I'll just write it here. I need p of x and h of x. Okay. Well, h is right here. Okay, starting from here all the way up here. Okay. So that's in fact h of x. And luckily, maybe we don't need to write them separately here. Luckily, since we said that the slice is like x units far from the axis of the revolution, I can go ahead and then call this x to be p of x, okay? Because that's going to be the radius of the bottom. All right, so we can see from the graph that the line, this purple line is y equals 8. So the distance from here to here is just 8. And again, from the graph, we can see that the bottom of the slice touches the blue curve. And since we're x units far from the y-axis at that point, so this distance from here to here is governed by the blue curve, and that is x cubed. Okay. All right. So then what is h? H is going to be 8 minus x cubed. All right. So let's write them all here again. So p of x equals x, h of x equals x cubed. And let's also check the range for x within the green region. So I can see that all x's within the region are ranging from 0 to 2. Okay, let me just also write that here. Okay. All right, so I can go ahead and write down the volume of the representative shell. Okay, so that's going to be equal to 2 pi times the radius of the bottom, which is x. Oh, this is 8 minus x cubed. I'm sorry. This is 8 minus x cubed. And I have 8 minus x cubed dx. So this is the volume of the representative disk, but we have a lot of slices, vertical slices within the region, and we're going to integrate this expression here from 0 to 2 to get to the volume of the whole three-dimensional object. I showed you at the end, right, like this one. Okay. All right. So to find this volume, I gotta integrate. And I go from 0 to 2, the volume formula. So x, 8 minus x cubed, and dx. All right. So let's simplify this real quick. This is 2 pi 8x minus x to the 4th dx. Okay. So 2 pi, let's find the antiderivative in one shot. This is 8x squared over 2, so 4x squared, minus x to the 5th divided by 5. From 0 to 2, we're using the fundamental theorem of calculus. All right, let's plug in 2. So 2 squared is 4, 16, minus 2 to the 5th, which is 32, minus 2 pi. When you plug in 0, it's going to be all zeros. Okay. All right, if you simplify that, this is 96 pi over 15. Okay. So here we go. I go ahead and write down that 96 pi over 15. What is that exactly? That's the volume of this three-dimensional object. Okay. Again, we were using the shell method, and we made use of the advantage of that. In fact, the function description provided to us is given in terms of x. So it was y equals x cubed. So having like a dx type integration makes a lot of sense. And all we need is the radius of the bottom and the height of the shell. All right. Well, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.